if it can serve as a relief, I was just trying to squeeze the very latest results into this presentation, so you should be proud that you are the first to see whatever comes out of the furnace, red hot.
Okay, that's very nice. But you weren't able to send me the slides, right?
I did. I mean.
You did.
Yeah.
Because
we
have this policy of. Yeah, they are okay. So then
I did like 15 seconds ago.
Yeah. Okay, so then I'll introduce you. You start, and in the meantime, I will put upload the slides. So yeah, it's very nice to have Alexander Krikun from Nordita, who, as he was saying, he's going to tell us these very last interesting results about coherent and incoherent transport in holographic models with dynamically broken translations. So please, Sasha, go ahead.
Yeah, thank you, Daniel. Thank you very much. And yeah, thank you for inviting me for this very nice initiative. I think really, I mean, I was thinking lately that HoloTube provides a format which was, I mean, it doesn't have an analog in the normal life. So it's really a good idea to just keep it running, whatever happens around. Yeah, and so I really appreciate the opportunity to give a talk here. So today I will give a little bit of overview of what's going on in the realm of holographic models with translation symmetry breaking, and I will particularly focus on the models with spontaneously broken translations. And in the very last moment, I actually decided to change the title a tiny bit because I want to stress that in those models which are considered, the translations are broken dynamically. So there is a dynamics which leads to phase transition. You can actually, it happens not only spontaneously, but there is also a mechanism for it. When you cross a particular critical temperature, the new phase with spontaneously broken translations emerges. Right, so this is like the work which I will present now has a long history and has traces in all the, I mean, almost all my works which I've done for the last few years with all these nice people. I want to stress in particular the contribution of Tomas Andrade, who's always appearing in all these works. Also, I should point out Floris Balm, who is now a PhD student in Leiden University and who developed very serious machinery which we are using now to address complicated numerical questions. So Konrad Schalm and Jan Zanen, they lay down ideology behind all this work. And also I should mention the specially invited star Matteo Baioli, who revived somewhat our interest to this subject not so long ago. And there will be more works to appear soon, so keep tuned. So I will first introduce what is dynamical translation symmetry breaking. I expect that most of you know about these things, but it will be important for me to just keep us on the same page because I want to stress particular points and focus on them. We'll discuss how the metal-insulator phase transition looks like when you can see the models with spontaneous symmetry breaking on top of some explicit sources. I will discuss how coherent and incoherent transport behaves under these phase transitions, and what role is played by coherent and incoherent parts of the transport. It turns out that the hydrodynamics of charge density waves and the scale of phase relaxation plays a very important role in all this physics, which I will discuss next. And in the end, I will show some these red hot results of the ongoing project. Yeah, I again apologize that that section might look a little bit incomplete because the work is incomplete, but I think it sheds some new, very interesting light on this whole business. And I should also say that I very much appreciate the feedback from you because it's a work in progress, and it's important for us to understand how to look at all the data which we obtain. So let's start. What do we mean by dynamical phase transition? Oh well, okay. Motivational slide. So why do we care about translation symmetry breaking holography? So that's because firstly, our aim, our dream is to use holographic models to describe some features of non-Fermi liquid condensed matter, some strange behaviors which are observed in some materials, and the most famous representative of this family is cuprate high TC superconductors, and the phase of strange metals, which is seen there, which is considered to be non-Fermi liquid, and which has some peculiar features in transport as well. Why do we want to focus on spontaneous symmetry breaking? Is because these cuprates, they are known to be doped Mott insulators, and I will mention that Mott insulator can be understood as a pinned spontaneous charge density wave. And the charge density wave plays an important role in the physics of these materials, it looks like, because it shows up in different corners of the phase diagram. It prescribes, it might prescribe the ground state of these materials, which is a doped Mott insulator. And on the other hand, when we study holographic models with spontaneous symmetry breaking, with charge density waves, so they present few interesting features which are not exactly the same which you would expect from the conventional physics of charge density waves. And it is always important for us to focus on the features which are not exactly the same in the conventional physics, because it might be useful to describe some unconventional experimental results which are seen in nature. So that's why the subject is interesting, and that's why many people are focusing on this. Right, so with dynamical translation symmetry breaking, we can, well, roughly speaking, you can think about it as the phase transition, which is driven by an unstable mode which appears in the spectrum at finite momentum, at finite wave vector. So if we think about starting from the Bryson-Orson black hole, for instance, with some particular field content, we'll see that at certain critical temperature. Do you see my pointer, by the way? Or should I use the red one?
We do. Don't move it too fast.
So this type of bell curves you can see in various models. And basically what it shows is that at different temperatures, there is an unstable mode in the spectrum at different momenta, a different wave vector. That means that when I lower the temperature starting from very high, at critical temperature, which is here 0.15, I will hit the first unstable mode. And this unstable mode, being at finite momentum, it will source the ground state, which is spatially modulated. And because the ground state is spatially modulated, this ground state will break translation symmetry breaking spontaneously. And once I hit this, once I hit the unstable mode, it grows And you can see the red line here. Inside this bell curve, there is a new family of nonlinear periodically modulated solutions which you can obtain. And these are the spontaneously broken states, which are driven by the unstable mode. This is what I mean by dynamics. So I can always trace the critical temperature. I can study the spectrum of model there, and I can study how the phase transition happens by following the marginal modes in the spectrum. And today I will focus on two models which share this feature of dynamic translational symmetry breaking. One of them is Bianchi 7 helical model, which was, I think, the first holographic model to discuss translation symmetry breaking. So this is based on 5-dimensional bulk space. You have here a gravity sector, and you also have a Chern-Simons term. And this Chern-Simons term drives the instability in this model. So you see that yeah, so at some temperature, there will be this second component of the gauge field, which is proportional to the helical mode, which is shown here. You can see that this helical mode is x-dependent, so it breaks translations in x direction. However, like those modes are arranged in such a way that they break translations in this helical way, so you can actually always unwind this. So if I perform the translation in x direction, and simultaneously I perform a rotation in y and z direction, then the symmetry will be restored. So this model is a member of the family of so-called homogeneous holographic lattices, the family to which linear axioms and Q lattices also belong to. So there is a linear combination of the other symmetries which get which is kept untouched by the spontaneous structure which emerges. But for us, it's not important right now, because what's important for us is that the translations along x direction is broken. So if we forget about, if we don't focus on the extra rotation, etc. And this is broken by the unstable mode, which is just the A2 field, the component of the gauge vector, which is proportional to the second helical mode. And once this unstable mode arises in the spectrum, this helix starts building up in the nonlinear solution, and you end up in the ground state, which breaks translation spontaneously. This is depicted in this slide. So again, there is a critical temperature, there is a particular pitch of the helix, which is non-zero. We hit the unstable mode, and then on the red line, the family of nonlinear spontaneously broken solutions live. On the right-hand side, you can see the order parameter for the spontaneous symmetry breaking. And this is the mean value of the second component of the current. So the current which is associated to this gauge mode. You see that it is 0 above the critical temperature, and then it quickly builds up. So this is basically the second order phase transition which we see here. Another model which I also want to discuss is the model with periodic lattice. So this one is a little bit less weird than the helical one, because this one just describes the honest-to-God periodic structure. So it lives in 4 dimensions. There is an Einstein term, there is a Maxwell term, and importantly, there is this theta term in the action. So, and the theta term, if I write it out, it consists of the field psi. So psi is an axion field. It's a scalar with a particular, with a negative parity. So if I write out this term, it consists of the scalar, the x derivative of the AY field, and the radial, the holographic derivative of the time component of the gauge field. So this dz AT part is non-zero as long as the chemical potential is non-zero. So if I have finite chemical potential, then there is some finite profile to the AT field. There is finite z derivative to it. So this part is finite. And then I just have the interaction between psi and dxay. So now the unstable mode is a composite mode. It consists of psi field, which oscillates as a cosine kx. Yes, sorry, there shouldn't be I here. It's just cosine kx. And the transverse current field, which oscillates as sinus kx. Again, the bell curve, you've seen this already. It starts at a critical temperature, and once we cross this point, we see that these psi field and AY field, they acquire some vacuum expectation value, and these expectation values, they are position dependent. Again, the translations are broken spontaneously. However, in this case, unlike helical model, there is no extra symmetry, there is no extra rotations or anything, which would allow us to treat this model in any kind of homogeneous way. So in order to really solve for the backgrounds in this model or consider any kind of linear response, one has to do proper partial differential equations, which is a tiny bit complicated, but it's only a technical issue. Another advantage of this model is that because the profiles are truly periodic in the spatial coordinate, that this model introduced the proper brilliant zone in the ground state. So, and we had a few works about this. So, for instance, if you consider the spectrum of fermions on top of this model, we get a proper Umklapp scattering and all the familiar features of condensed matter theory book. We also, it is also quite convenient to use this model because of this brilliant zone structure, you can make direct connection to what condensed metal people are usually talking about. So this looks like the most physical one which we have at hand.
Sorry, can I ask a question?
Yes.
Yeah. I'm Carl. I don't know if you.
Yeah.
Yeah. What sets the value of K in the ground state? As far as I remember, in the Chern-Simons model, right, there is a critical value for the Chern-Simons coupling.
Yeah.
For its ability to exist. So Chern-Simons coupling has to be larger than a certain critical value for that. But in this model, what sets the critical value of K in the ground state?
Yeah, it's basically the same. It's C1. So
I see.
It's a factor in front of theta term.
I see. But it's okay. So is this in some sense like a dimensional reduction of the previous model? It looks a bit like that.
I mean, yeah. I also tend to think this way. However, it was never done. I mean, it would be nice to understand how to think about this model as dimensional reduction. So maybe, I mean, I would imagine that if I just cut this helix and I completely forget about z direction, then I would just see cosine and sine. So, I mean, yeah, they are very similar to each other.
So is there also a critical value for the C1 parameter?
Don't remember actually whether there is a critical value, but clearly, so critical both critical temperature and the values of critical K, they depend on C1. So the larger is C1, the larger is critical temperature. And for very small C1, I think, well,
Actually, it also depends on the chemical potential, right? You need to find a density.
no, yeah, that's true. I mean, it's
combination of values, I guess.
Yeah, that's right. But it looks to me that for any C1 there will be a phase transition, but I cannot prove it right now. But, okay, like philosophically, this type of symmetry breaking phase transition always exists when you have this type of interaction, when the interaction between two modes, the unstable modes, includes the derivatives. So then once you, this is term which is linear in derivatives, and then you have, when you diagonalize the matrix of the unstable modes, you will see some factors of K minus something, which sets the effective mass of the unstable mode. So for finite K, you will see the mode which is most unstable, roughly speaking. Any questions about this model? Okay, good. So yeah, there are two examples which we know, which are available since long ago, and they developed this dynamical instability and form the spontaneous ground states. And it's quite interesting to consider the transport in these models. But as we understand, since the ground state of this model, since the normal state of this model doesn't have any kind of phase translation symmetry breaking, then that means that the normal state of this model is ideal metal which doesn't have any resistivity. So in this regard, this model without any explicit translation symmetry breaking is very boring from the point of view of transport. So if I want to consider transport in these models, then I want to introduce some explicit symmetry breaking source. And this can be done in both models. So for helical model, I can introduce the extra B field here, and I can prescribe a source to the B2 component. So you see that the B field is the extra gauge field, which enters practically in the same way in the same Lagrangian. I can write down, I can prescribe a source to the B2 component, and this will break translations explicitly because there is a source here. But it will break translations in precisely the same way as the translations would be broken by A field, by the spontaneous mechanism. So if I introduce my explicit source in this way, I still allow for the dynamical phase transition in this model. Besides the fact that the translations are already broken explicitly, the dynamical mechanism which drives instability still exists here. So it gets sloppy to talk about spontaneous symmetry breaking because now the symmetry is not broken spontaneously, but the phase transition exists. And one can talk about pseudo-spontaneous phase transition or the symmetry which is broken approximately spontaneously when this explicit source is not too large. But what's important for me from the observational point of view, once I have some explicit symmetry breaking scale, then my normal state of this model is doesn't have infinite conductivity, so it has some finite conductivity, and I can measure it and I can study it. And what I see in this model is quite interesting. So above the phase transition, there is some conductivity which is quite high if my explicit source is not too large. But then when I hit the critical temperature, the conductivity drops dramatically. So it's a very sharp drop here. And really, if you follow downwards this curve, you will see that it keeps falling down. So the system really undergoes the phase transition between the metallic behavior, where conductivity was growing when I lower the temperature, to the insulating behavior, where the conductivity decreases when I decrease the temperature. This is a true metal insulator phase transition which happens here.
Okay,
Sasha?
Yeah.
Hey, it's Blaise.
Yeah.
Can I ask? So in your previous slides, you have to introduce this extra field in order to incorporate explicit symmetry breaking. But would there be any qualitative difference if you turn on a small source for A2, which you could also do? For instance, compared to the next plot that you showed for the conductivity, would you get anything qualitatively different? Or same with the dependence of various things on the explicit scale?
I wouldn't expect this. I mean, I think like the statements which are made are, I mean, they're so general that I don't expect them to be dependent on the particular way you break translations. So you can in principle get away with just sourcing a field, I think. But then it will, I mean, I personally prefer to use a different field because sourcing a field complicates the analysis of instabilities.
Okay.
I mean, then I need to be extra careful in order to see whether right. So if I would source A2 field explicitly, then I would not be able to treat this J2 thing as order parameter, because J2 will be sourced everywhere.
Yeah, so it might not go exactly to 0 above some TC, but most likely for a very small source, you would have a continuous interpolation between your blue curve and then close to the TC on your plot. It might flatten out and follow the yellow curve, something like that.
You mean this? Yeah. Yeah, pretty much.
So, you know, the details will change, but
it will hide the mechanism which I'm hunting for. So I mean, it will be still there, but it will be harder for me to disentangle two things. So I want really to, so again, so the word of the day is dynamical. I want to follow this dynamical mechanism and keep it as clean as possible. So,
okay, maybe I'll ask again at the end of the talk.
But I agree with you.
A quick question. This is still homogeneous space. Do you have to solve partial differential equation or just ordinary?
In homogeneous, it's easy. In homogeneous, it's just ordinary differential equations.
Yeah, but it is explicit symmetry breaking is still homogeneous space.
Yes. I mean, if you are careful about keeping explicit source on the same wave, helical pitch as the spontaneous structure.
The big deal is that when you're dealing with an homogeneous space, I protest as a condensed metaphysicist against calling this translational symmetry breaking. Right? The issue is that the rotations are semi-direct in translations, and my prejudice is actually that it's all about, at the end of the day, rotational symmetry breaking, right? It's a Bianchi space which is anisotropic but homogeneous. Right, when there's no umklapp, I protest against calling it translational symmetry breaking. It's a bit of a semantic thing, but this is never of relevance to condensed metaphysics.
I think if we let him continue, then the point of his talk is to show that things are quite similar in both models.
No.
Give him time. Give him until the end of the talk.
I know exactly how these helical symmetry breakings work, and you guys are just sloppy. This has nothing to do with what.
So I think that by the end of the talk, he will show you plots that are qualitatively similar in both types of models. So let's let him go on.
Better listen to condensed metaphysicists instead of dreaming away with simple solutions.
I agree with Jan. I mean, we can call this model whatever we like. This is just an example which shows some spontaneous formation of some structure. Let's keep it like this, and that's fine. So we can immediately go to explicit lattices. I mean, for periodic lattices. So, and in the periodic lattice, it's even easier actually to introduce the explicit source. Oh yeah, sorry, I didn't. I wanted to complete my answer to Blair. So I don't expect that all these qualitative things will depend on how you source, how exactly you source explicit breaking. So I do it for convenience my way, but you can do it your way if you wish. So right, the same story goes through in proper periodic lattices, which break translations in an honest way and that which require real partial differential equations to be solved. So I can introduce the modulation of the chemical potential, which goes like cosine kx. This is a snapshot of the background of the full gravitational solution, how it looks like without spontaneous structure. So the modulation is sourced on the ultraviolet boundary, and then it slowly dies out towards the infrared horizon. This is a source for explicit symmetry breaking. And I can introduce it in my model. And the model, since there is still an instability in the equations of motion, there is still this dynamical mechanism of creating the spontaneous structure. So the model, which still undergo the phase transition at some critical temperature, and it will show this type of behavior. So above the critical temperature, again, there is some conductivity, which is finite. And once I cross the critical temperature, it drops again quickly and dramatically in this discontinuous fashion. Very cool. So same thing. Why does it happen? Like what precisely happens here? This we understand actually quite well already, which is the physics of this metal-insulator transition is more or less well known. So we can understand it from the point of view of broken symmetries. So when I have the spontaneous symmetry breaking, I have a Goldstone mode in the spectrum, which is massless. But once I introduce the explicit source for the explicit source for the same symmetry breaking, this Goldstone mode becomes pseudo-Goldstone and acquires some finite tiny mass. So the best example, which I know from normal physics, is a pi meson from QCD. And, some of us know about it much better than I do. So pi meson is a Goldstone boson of chiral symmetry in QCD, but it still has finite mass. So the mass is 10 times lower than rho meson, for instance. So it's relatively light, but it's finite because chiral symmetry is not exact, because chiral symmetry is broken by the masses of quarks. So here, in this story with translation symmetry breaking, basically observe the same mechanism. So there is a Goldstone mode associated with the spontaneous mechanism, but because the symmetry which is spontaneously broken is not exact, the Goldstone mode acquires a mass. And you can see it on the plot of AC conductivity. So this is AC conductivity for the helical model. Above critical temperature, you see this purple line. This is a beautiful Drude peak. But when I lower the temperature and go below critical temperature, I see that this peak gaps off, so it goes away from the origin. So it acquires some finite mass. This is the mass of the Goldstone mode here, which we see emerging. So when I go lower in temperature, the order parameter grows, and with order parameter, the mass of the pseudo-Goldstone boson grows. And of course, you understand that basically this drop here is associated with going from the top of this sharp peak to the shoulder of this sharp peak. And of course, it happens quite dramatically and quickly. So the same, I have the same pictures of the periodic model, and the periodic model basically behaves in the same way. I have here the sharp Drude peak, and when I lower the temperature below TC, I see that this peak gaps off. So very nice. This is a very important finding, because basically tells us that, I mean, if it would be, yeah, so this mechanism of metal-insulator transition is well known in condensed matter as well. And there it leads to complete suppression of transport. So it really goes from finite transport to zero. So the gap opens in the spectrum of charge carriers. You make the proper Mott insulator, and the system doesn't conduct at all. However, what we see here in our holographic models is a tiny bit different. So we see that the DC conductivity after this phase transition actually stays finite. We know that in holography, there are two contributions to conductivity. One is associated to the momentum, has some overlap with momentum, another doesn't. So when I play my games with translation symmetry breaking, I really only affect that part of conductivity which does overlap with momentum. So momentum was weakly conserved above phase transition, then it gets gapped in this pseudo-Goldstone mode, and then the contribution from momentum is very much decreased in the coherent part of the conductivity, but there is also incoherent conductivity in holography. And incoherent conductivity has very different nature. So it cannot be associated with current mediated by some particles, by some charge carriers, which also carry momentum with them. So this can be thought of contribution from quantum critical continuum, from production of some particle-antiparticle pairs in quantum critical theory, and et cetera, So the incoherent conductivity is extremely interesting. So this is something new which holography brings to life. And if it really happens that the finite tail here is purely incoherent conductivity, then this is very good news for us, because then we'll just go to experimentalists measuring cuprate high temperature superconductors, and we ask them what is the conductivity of these systems when the charge density wave is formed, so when the translation symmetry is broken both spontaneously and explicitly. And then I know that whatever you measure there, you measure precisely the features of this quantum critical continuum predicted by holography. So if this idea is true, this is extremely important for both understanding behavior of cuprate superconductors and holography as a tool to predict something interesting. However, it turns out that the situation is not so simple. Because if I just blindly measure the DC conductivity, the DC electric conductivity, and DC incoherent conductivity in my holographic model, and there is a formula for measuring incoherent conductivity. It's quite robust, and you can evaluate it for all these backgrounds quite easily. So you can see that incoherent conductivity, and so here I plot both of them. And take a look that the scale here is logarithmic scale. So the fact that these two are apart from each other is very dramatic. So one of them is like 10 times smaller than the other one. So this DC contribution below the phase transition is mostly coming from coherent part of the spectrum, not from the incoherent one. So what I see here is still the feature of the transport, which one could call normal transport. So the transport associated with momentum, relaxation, momentum, conservation, etc., etc. The transport which could be mediated by particles which also carry momentum. And the incoherent conductivity doesn't play a lot of role here. However, this plot is also surprising because based on the logics which comes from the condensed matter theory of charge density waves, we would expect that the transport is gapped completely, because like once the charge density wave is formed, the spectrum of the quasi-particles is reshaped, the gap is opening in the Fermi surface, and there should be no carriers which could carry any momentum, any current in this state. However, in our models there is some. So where does it come from? Yeah, by the way, this is a plot again for helical model. This is the plot for periodic backgrounds. They show the same features. So the DC conductivity is not fully accounted for by incoherent part. There is still coherent contribution to DC conductivity.
Sasha, may
yes.
I ask another question? So in this plot, so in particular in this last plot, can you remind me, so do you evaluate this both directly in the DC limit and also checking the degrees with taking the small frequency limits?
Yes.
Is there any chance? Yeah. And the
No
discrepancy
chances.
you see is not,
So this is, yeah, that's quite robust. So basically, if you want, the way I understand that my incoherent conductivity is correct is that I see in AC conductivity that it takes into account all the tail correctly. So it just shares off the peak. So my AC, so the AC incoherent conductivity is precisely doing its job. So it completely neglects the peak associated with momentum conservation, takes into account everything else. Now I can evaluate its DC limit, and it ends up being in the same point as the one which I would evaluate directly in DC limits. So, right, yeah, small frequencies of AC give the same results as DC calculation by Stokes on the horizon. So I would say that this result is quite robust, and I mean passes any checks I could imagine. Yeah, but okay. So where does it come from? Where does the discrepancy come from? This is now we are entering some realm of new physics, say, because this would be the discrepancy is not expected in the normal, yeah, from the normal condensed matter point of view. So the answer comes from the formula developed by Sean and Blaise and Luca. I mean, developed, written down. So basically, what if I build up some hydrodynamic approximation to the hydrodynamic treatment of these charge density waves and approximate conservation of momentum and Goldstone modes and etc., etc. So then I end up with a formula which looks like this. And it's simple enough. So my conductivity can be split into two parts. One is incoherent conductivity, which I have no idea about. I mean, it's just some quantum critical result, plus something which is a coherent conductivity which has an overlap with momentum. And there are a few important things here. So there's gamma, which measures the explicit, which measures how much the symmetry is broken explicitly. There's omega naught, which is the effective mass of the pinned Goldstone mode. So this is what we this is what we saw in the previous plot. So this is the position of this gapped peak, and omega naught is proportional to gamma multiplied by the order parameter, which develops in the spontaneously broken phase. And there is also capital omega. So capital omega is, you can call it effective phase relaxation rate, whatever. I prefer to call it capital omega because just not to involve too much physics in it, but it's there in the formula. So basically, yeah, it is there because it can be there. So if I just take this formula and evaluate the DC limit, then I will see that for explicit lattices, this is just 1 over gamma. This is Drude peak, which is fine. And for spontaneous lattices, I will see that there is a remnant of the coherent part. And this is proportional to this capital omega divided by omega naught squared. In other words, these results for DC conductivities show that this mismatch between coherent and electric DC conductivity is caused by this capital omega, by the effective relaxation rate. Okay, I should also make an extra comment here because in, yeah, sorry, that's the careful pronunciation of this formula also includes the extra factors here in the numerator, which is proportional to gamma 1, and gamma 1 has something to do with the correlator of Goldstone modes in this whole hydrodynamic theory developed by Blair. So in principle, this capital omega, which enters here, can also get contributions from gamma 1, which is an extra hydrodynamic parameter. So right now, we don't really know whether it is phase relaxation rate which is responsible for this discrepancy, or whether it's gamma 1.
Quick question. I've been staring at the equation, but I tend to have a bit of a struggle. So I would like to understand that when you ignore the gamma 1, it's basically what's called a Drude-Lorentz type model, where you say that there is an overdamped oscillator living at omega naught, having a width of omega, spilling out to 0 frequency. Is that correct? Can I think about it? Omega, what is it? Is the width, and omega 0 is the position of the overdamped pole.
It's kind of crucial. I think that you can sort of think of it this way, except that usually when you do Lorentz fits, then you don't have a capital omega term in the numerator, so that your Lorentzian fit goes to 0 at 0 frequency, but here it doesn't, because when you write down the constitutive relations for hydrodynamics in presence of this phase relaxation rate, then you still get it in the numerator. And as you're saying, this is why it's leaking all the way to 0 frequency, as we can see on the last line of this slide.
Right, so for purposes of using my eyesight to interpret the data, I can think about it as there is an overdamped oscillator with an energy omega naught and a bit omega, and I'm safe. Or is there still something else going on?
You can, the way I tend to think about it, which I think is very close to what you're saying, is indeed you have this oscillator that lives at omega 0, but omega 0, this is generated by the explicit symmetry breaking mechanism, whatever it is. It gives a mass to this Goldstone because you're explicitly breaking the symmetry of which this is the Goldstone mode.
Yeah.
But then it also makes sense that the same mechanism is going to give this mode a finite lifetime.
Yeah.
You don't just have a Dirac, Dirac comb, you have a width.
More primitive footing, just trying to understand the formula just purely phenomenologically. Can I get away thinking that overdamped mode has really a Lorentzian line shape, or is the line shape somehow screwed because it's a bit more complicated than just Lorentzian?
I mean, because of the non-trivial numerator, it's not precisely Lorentzian. That's very important part, actually.
Yeah.
So the denominator is just a damped oscillator, but numerator plays an important role.
When I ignore, right, so there's no gamma in your sigma DC formula. So a good feeling when you ignore gamma, that I'm more or less right. It's the claim that it's just an overdamped oscillator.
There should be a gamma.
Excuse me?
There should be a gamma in the formula on the last line. It's just that Sasha neglected it.
Oh, in the sigma DC formula.
Yes,
Yeah,
the
right, so
denominator should have a
you can
gamma.
that's that simplified formula. Then I can think it's an oscillator, but when it's gamma dependent, it's a bit more complicated. It's not quite Lorentzian.
If your Lorentzian is very strongly pinned, so if omega 0 squared is very big compared to gamma times omega, then you can neglect any contribution from gamma.
I'm fine.
Yes, but okay. So now we can once we look at this formula. So the question which immediately comes in mind actually is, how can what should I think about this capital omega thingy? Like whether I can imagine the physics which gives rise to it, and where does it come from? And the thing which puzzled me in particular quite a lot is the following. So suppose this formula is just correct description of what's going on. Then it means that besides, and suppose I will look in my system very close to critical temperature. So very close to critical temperature, this G2 factor, the order parameter, is close to 0, so it's very small. So omega naught, yes, there should be omega naught here. Omega naught is also extremely small. So there should be two imaginary quasi-normal modes here. One is sitting at I omega, another one at I gamma, another one is sitting at I omega. But on the other hand, so this formula predicts right below the phase transition two purely imaginary quasi-normal modes. Like I understand where's gamma mode coming from, so this is just diffusion of momentum because momentum is not exactly conserved. But I don't quite understand the physical meaning of capital omega thing. However, if I go above the critical temperature, then this omega naught precisely vanishes, and this term this term proportional to capital omega in the denominator is cancelled by the numerator. So there is no capital omega mode anymore in the spectrum. So it looks like this quasi-normal mode just disappears, which is extra weird because, quasi-normal modes should not just simply disappear, right? And that poses extra questions of whether this capital omega is physical at all and whether we should consider it carefully, and etc., etc. So what we decided to do is to precisely make this exercise, study these models, which I have here, and study this phase transition region around critical temperature and follow the quasi-normal modes which you get from this formula.
Sorry.
Which you get from the data and match it with the formula. Yes.
Can I ask you a question? Maybe I'm lost now, but are you sure the QNMs have to always be purely imaginary? Because as you well know, in the models we looked at, the QNMs have a real part. Now just staring at the formula, maybe saying a stupid thing. What I remember from at least Bless' formula, he can correct me, is that the QNMs are not always purely imaginary, right?
Oh, that's true. That's absolutely true. That's the feature of this damped oscillator. So
okay.
when omega naught is sizable, when it has any, when it is finite number, then omega naught gives you a mass, and this mass gives you the real part of the quasi-normal mode.
Okay.
But if omega is very small, if omega naught is extremely small, then both solutions to this to the denominator, they are imaginary. So it will be, they are roughly gamma minus omega naught and minus capital omega plus omega naught. And when omega naught grows, these two imaginary poles, they come together, they collide, and they form a pair of real valued
Okay.
complex
That I agree.
But it's not entirely
pseudo-Goldstones.
clear that you can tweak omega naught independently from capital omega. I don't think that in general you'll have a parameter that, yeah.
I mean, there is no any indication that capital omega depends on the order parameter.
No, not order well, if you kill the order parameter, then you have no capital omega either. It's not just that I mean, all of these things, they go to zero if you go away from the limit where there's a spontaneous symmetry breaking going on.
So
right?
This is the news, I would say. It's not true. So, I mean, if it would be true, then it would be really an physical situation. I mean, if above critical temperature, capital omega doesn't exist at all, like as a concept, like never existed, right? Then I need to admit that the spectrum of quasi-normal modes is discontinuous at critical temperature. I mean, spectrum of quasi-normal mode being discontinuous is very dangerous statement. I mean, I don't understand how it can happen from the point of view of, you know, just the theory of differential equations. I mean, there should be, the spectrum is always continuous as long as you change the parameters smoothly. And the critical temperature, all the parameters of all the equations are changing smoothly because this is second order phase transition, and the background solution changes smoothly. So the equations which govern the quasi-normal modes, they should also smoothly change. So I do expect this quasi-normal mode not to go away. However, in this formula, it just disappears. And the question is, how does it happen?
Sorry,
right.
Sasha.
Yes.
If you were to do superfluids, you could make the exact same comments about superfluid second sound. You have an extra QNM there.
Yeah, I think I can answer that.
Yes, I was thinking of you.
Yeah, okay. So what's happening is that there, you know, in the simplest model, which is not backreacted, you have two scalar modes from the charged scalar, and you have one diffusion mode in the symmetric phase. Okay, and they all come together, and then morally speaking, the two modes which come from the scalars, they become second sound. They have both real and imaginary part, and the diffusive mode goes through, and it's not stays at omega equals 0 for 0k, but now it has a finite imaginary value below the phase transition, such that below the phase transition you have just the two hydrodynamic modes, whose origin are, so to speak, the two scalar modes in the symmetric phase, and the diffusive mode, which was the single hydrodynamic mode in the symmetric phase, it's not hydrodynamic anymore. So it's three modes, they all come together, and at the phase transition point, they all are hydrodynamic. But the number of modes doesn't change.
Yeah, I think in here we actually observe the same thing. So let me unveil a little bit and don't be too mysterious. So you can see actually in this formula. So the mode cannot just go away. However, it can decouple from the particular two-point function. So this sigma measures the two-point function of currents. And what we see here is that the coupling between capital omega and the two-point function of currents is governed by this numerator. So once the numerator goes to 0, the quasi-normal mode doesn't appear anymore in the spectrum of the two-point function of currents. So below the critical temperature, when you build up the order parameter, this order parameter couples capital omega to the current transport, and that's why you see it appearing in this formula. But above the phase transition, there is no order parameter, and wherever this capital omega comes from is not coupled to the transport of current. So this is like these scalar modes, which which Carl was talking about just a second ago. So let me show you. Remember, I was telling you that the phase transition is always driven by some modes, and these modes are like on this slide. Like in case of helix, this is omega-2 mode. In case of periodic lattice, this is psi and AY mode. So there are modes which drive the phase transition. So now let me measure the quasi-normal modes in different channels. So what I do, because there is also a picture by Thomas in the helical mode, but shamefully I couldn't include it in the presentation because it was in the wrong format. But anyway, the physics is the same. So here's this is a picture which shows the quasi-normal modes of the system on the imaginary axis. So the vertical axis is just the imaginary position of the quasi-normal mode, and the horizontal axis is the temperature. The grid line here shows the critical temperature. The colors mean, so how do I obtain this quasi-normal mode? In periodic lattices, it is quite hard to solve the eigenvalue problem for the linear equations of motion. This is huge. But what I can do, I can measure the two-point correlation function at imaginary frequency. So I can just measure it on the imaginary axis. And if I measure this two-point function at imaginary axis, I will hit these poles like head-on, and I will see that this two-point function just diverges in these points. And in this way, I can extract the quasi-normal modes which are lying on imaginary axis. Is it clear enough? Like how it is observed? Right. So if I measure the conductivity, the two-point correlator of the currents, I will hit two poles below the critical temperature. But I can also measure different two-point functions. And on top of the current correlation function, I can also measure the psi AY correlation function, the correlation function which is responsible for the unstable mode in this system. So here you see the position of quasi-normal modes on these two channels in periodic background. So I'm crossing the phase transition point. The yellow diamonds show the poles which appear in unstable correlator, in correlator of unstable modes. And the blue points, they show the poles which appear in the correlator of currents in conductivity. So the first thing to pay attention to is this line of diamonds, of yellow diamonds here, which goes to 0 precisely at the phase transition and then goes back. What is this? So this is precisely the mode which drives the phase transition. So you see in the normal phase, there is a mode which above the critical temperature is damped, but once I reduce the temperature and hit the critical point, this mode becomes marginal. And this is precisely the mode which forms this bell curve, which I showed in the very beginning. So it becomes marginal, it drives the phase transition. And once the phase transition happens, this mode goes away. So it leaves the hydrodynamic spectrum. On the other hand, also in the normal phase, in blue dots, I see this line of points which are almost constant. So this is the Drude peak, because in this particular example, there is some amplitude for explicit symmetry breaking. So there is a Drude peak and there is a finite capital gamma, and you see it in the current correlator. So this is, in conductivity. Another thing to pay attention to is the second branch of the quasi-normal modes in this unstable correlator. So it is there. And once I cross the critical temperature, all the modes become coupled because of the finite order parameter. So now currents are coupled to the unstable modes and vice versa. And here, the second quasi-normal mode appears in the correlator of currents. So this is precisely the capital omega mode, which was not there on one side, but then it suddenly appears on the other side because the coupling with this extra unstable mode becomes non-zero. And then it does the usual business. So this branch of blue dots is not just capital gamma. This is capital gamma modified by omega naught. And this branch is not just capital omega. This is capital omega modified by omega naught. And when I drive the temperature a little bit lower, they come together and eventually they will collide and form a pair of pseudo-Goldstones. So you see, interestingly enough, in these periodic lattices, and actually the story in helices is precisely the same. I cannot show you the picture, but it's basically the same story. Even the position of quasi-normal modes here is well described by the same formula. However, now we understand much better what does this formula showing. So this formula shows that below the phase transition, the transport gets coupled to the system which was driving the phase transition itself. So these guys are precisely the fluctuations of the order parameter above the critical temperature. So you can easily think about them this way. So just above the critical temperature, the spectrum of model is not just the spectrum of the model without any spontaneous mechanism of translation symmetry break. This model already knows that there is instability approaching. So there are fluctuations of the order parameter, which you can see in the hydrodynamic description. So below critical temperature, because of the order parameter, they will couple to transport, but here they don't yet. And since there are two modes in this system, one of them crosses this line at finite imaginary position and plays the role of capital omega now. So in the end of the day, it looks like capital omega, like treating it as as being connected to the oscillations of order parameter is a very sensible idea because it really follows from somewhere there. I would maybe stop my presentation at this point because there are there is only one extra slide. But this is the main message which I wanted to convey. So in our most recent study, I think we shed a little bit more light on this formula and where all these things coming from. And there is actually no mystery at all. It's just this, the dynamical system which drives the phase transition gets coupled to transport. That's how you get the extra capital.
Sasha, quick question. Can you go back? Yes. That's also a bit too late, right? So when I see this formula, I can also write it as, look at the second part, 1 divided gamma minus omega, that's just the truth part, plus omega squared divided by a big omega minus I omega, right? I'm basically saying I have two modes, both of them are over-damped root. One of them associated with momentum, the other one somehow associated with, these, approaching the phase transition from the metallic side. We know that you get this sort of pileup of speculators associated with the order that it will set in. And they're just mode coupled by omega naught. By precisely the same thing you say, right? So when I have two modes and I'm mode coupling omega 0, right? We have get precisely this, right? It's basically like this omega squared not divided by omega, big omega minus I omega is like the self-energy for your Drude mode.
Yeah.
And it gets somehow implicitly when Blaise and Chomley write the formula, they basically wired it in, right? Otherwise you won't get that formula, that the damped order parameter mode is mode coupling to the momentum sector. Makes sense.
So the way that this happens, and Luca can also comment, when you write the Josephson equation for the Goldstone mode, the coupling to momentum occurs through the fact that there's a non-zero bulk or shear modulus.
Yeah.
And actually the shear modulus is hiding inside this omega naught in the effective theory. So if you were to take the limit where the shear modulus vanishes, then this Goldstone mode would, or this mode, decouples from momentum and so also from the current, because now it's got no way of overlapping with any of these. And indeed, the effective field theory would just predict a Drude response, so purely a gapped, purely imaginary mode, which goes in the direction of what you're saying. Somehow, by turning on a non-zero shear modulus, which is what you do when you cross TC, then you couple this system to momentum, and since you're at finite density and momentum couples to the current, then this feeds through in the conductivity as well.
Now, what I would think is, this is, pretty much a very general formula in a way, right? And really in the numbers that, right? So the whole issue is that when you have a normal pinned charge density system, and we've seen millions of them in nature, right? And Mott insulators is the one where it's completely developed. Then when you get below the transition, the damping of the order bounded form of omega would rapidly disappear, right? So basically Goldstone boson below the pinned quasi-Goldstone boson, there's no way to go, right? There's no phase space for decay. And somehow in this holographic system, there's still ways to decay.
So your question is, why doesn't this omega contribution completely vanish as you lower T away from TC, as you go deeper in the condensed phase?
Normal pinning really means that, right? That the classical Goldstone boson cannot decay anything else below the phase system where the mode pins. There's sort of the crucial difference between.
Well, my intuition would be that this might depend on the model that you're looking at least in this homogeneous Q-lattice type models, where we control very well what the ground state is. And I know you don't like them, but we control the ground state, we know how things scale, and we know how to make this omega appear or disappear, or grow large or grow small.
To the power of 5 Mott insulators in nature, this formula is saying Mott insulators cannot exist. That's the issue. We know how these Mott insulators work, pinned density rate, commensurate density rates work, according to detail, right? And I'm just telling you there, the answer is that the damping of your classical Goldstone boson completely disappear and forget about a finite omega when you're deep in the pin phase, right? And in holography, that omega, big omega, continues to be quite large, right? Making it possible that things spill out to zero. There's the big. Guys, it's very bad, but I really have to quit because my dear wife basically serving dinner, and at 6 I have a next talk I have to listen to.
Let me show the last picture to you, Jan.
Okay, and
you've seen that.
I'll leave the meeting. I'm sorry about it.
So, the interesting question which remains open, I think, is how do we really get good control of the second branch of the modes in the unstable sector? Because if this branch disappears, for instance, so if it goes all the way to the origin, then I would not have any capital omega in the other side, like below critical temperature. And indeed, if I just blindly take my periodic lattice model and I crank up the explicit scale, the explicit symmetry breaking scale, very large, I will see that the electric conductivity goes all the way towards incoherent conductivity. So the contribution from the coherent spectrum decreases strongly. So it looks like increasing the explicit breaking somehow removes this contribution of capital omega from the coherent state. So it is still, the value of capital omega is still, I mean, it is dependent precisely on the system and on the way the spontaneous symmetry breaking happens. Because you see, the mode which drives spontaneous transition is this one. And the capital omega mode looks like an extra mode here. So it can be there. Or maybe when I crank up the amplitude of the explicit lattice, I can remove it completely. Maybe that's the room for Jan's argument. And basically, depending on the system which we're considering, this Goldstone mode either has some channel to decay or doesn't have some channel to decay. This is something which which is still under consideration, and we need to clear this up. Basically, what we know is that at critical temperature, the way phase transition happens is seriously affected by the explicit source. So basically, of course, it is different system which undergoes the phase transition. So the features of it will and can be different.
You might have a look at, we wrote a long time ago, a paper that was basically saying you can study these matters for holographic superconductors, and when you would be able to measure the pair susceptibility, right? I think it's a bit similar, right? Not the conductivity, but the pair susceptibility that later on start to talk to the conductivity. You find out that there is this mode, overdamped mode above TC, right? That approaches a zero frequency when you get at the phase transition. And it's very well known how this works out, but it's really related to mean field phase transitions that you can compute with RPA.
Yes, that's true, but it doesn't say anything about the second mode, about this one.
No.
Just,
be a bit of mystery. Right?
Sasha,
yes.
Correct me if I'm wrong, but in this model, when you crank up the lattice, the explicit lattice,
Yes.
this is when everything starts being commensurate.
Yes.
But then you don't, okay, based on the way I understand the EFT, then I wouldn't expect this omega mode to be there at all, because the omega mode is there because of the shift symmetry of the phase-on mode of your spontaneous lattice. But once everything is pinned to the explicit lattice, then the spontaneous lattice cannot move, it cannot shift. So indeed, you would expect this mode to completely to go away from your spectrum, to become so damped that it's not part of your EFT anymore. It's because everything is locked in, nothing can move. This omega really comes from the shift symmetry, or at least the weak breaking of this shift symmetry of this phase-on mode that you can have in incommensurate charge density waves. If everything is commensurate, I don't think you see it. And I think it's maybe also the answer to Jan's question about Mott insulator, because if you have a Mott insulator, then nothing's moving. Phonons move, but no charge carriers are moving.
That could be the case indeed, because when I think about how, like, what exactly does it mean to break the translation symmetry, there are two things which I'm breaking. So I'm breaking the scaling by choosing some particular period, but I'm also breaking the shifts. So this guy here, I think it should relate to choosing a particular period, because the period builds up at this point. So a particular value of the wave vector is picked by the spontaneous transition. This one may be indeed the second counterpart, the shift, which is maybe I very much agree with this. So basically, at small amplitudes, this is the damped shifts of the whole system. Well, at large amplitudes, this whole thing will go down.
Yeah, you didn't show this plot, but you have this plot somewhere in one of your papers, right? Where you see the commensurate lock-in as you increase the amplitude of the explicit lattice.
I mean, yes. I mean, we never discussed commensurate lock-in in terms of quasi-normal modes. Like, how would it look? So that's precisely the question which you're asking. I mean, that's precisely the question which I'm revisiting now. How this commensurate, how the phase transition looks in case when you have a commensurate lock-in. How it looks in terms of quasi-normal modes and all these things. So far we were just looking at the bare ground states and the free energies and all these things. We have also a paper about the position of the critical point. But so this, I mean, there's basically yet another evolution on the same subject. Like, how precisely does it look like, and what's the physical difference between this regime where you have some damping and that regime where you don't have any coherent contribution. So now with these results, I hope we will reach there quite soon.
Sorry, maybe it's a repeated question, but so what you're saying is the symmetry breaking pattern. Can I think that you are breaking translations cross some global shift or U1 symmetry to some diagonal? And then you are saying that this omega mode comes from the shift symmetry. Did you?
Because to bless, I believe.
No, no, because my next question was, can you do something different? Like maybe it's more complicated, but do a model where you, I think we discussed this, where you don't have this extra U1 and see, and do the same experiment.
I mean, but in this model, there is no any extra U1. Like there's no anything which you could call extra. So well, if you have a periodic structure building up,
call it whatever.
Shift of phi.
Sorry?
You have a phi shift.
I mean, I have my spontaneous structure and can move it around.
Yes.
This is a shift which you're talking
about. Let me put it differently. My intuition that I think also, I didn't make it up. It's in these papers by Nicolis and maybe others before him. I'm not exactly sure where the paternity goes, but somehow if you look at scales that are large enough, which is certainly the case when you look at these modes at small frequencies and small wave vectors, then even if your system is inhomogeneous, at least in this type of inhomogeneous system, you can still treat them homogeneously at large enough distances. And that requires the introduction of this shift symmetry, which gets broken by any explicit symmetry breaking. To me, it just goes to say that the same EFT applies to inhomogeneous and homogeneous models, which honestly, I don't find too surprising.
No.
But I'm not sure that Jan would have agreed with us, but he's gone now, so I can say it. So it's not that you don't introduce it by hand like we do in holographic models like Q lattices or Bianchi 7. You put the homogeneity by hand, but it still emerges in the IR, even in the inhomogeneous lattices.
Yeah, that's true. That was basically my statement. That this U1 is not an extra U1; it's a generic U1, which will always be there because there are shifts. So this is you cannot build up the model of translation symmetry breaking without shifts because shifts is translations.
Yeah.
there are two things. Yeah, I think the only question which remains here is that maybe you can break translations without introducing periodicity. Like maybe you can, like what will happen if you break translation by one nail? Like not.
And this was my question. By one what?
Well, if you just nail thing down in one point.
That sounds more like disorder.
Yeah.
That sounds very much like disorder, but in principle, from the point of view of group or whatever symmetries, it should do the same job, right? It's just explicit breaking of translations. But it doesn't have any elasticity associated. I mean, yeah, it doesn't introduce any period, so this period doesn't introduce any elasticity mode, and that maybe it will remove actually this line on this plot, because this line is really, I tend associated with the building up of the periods. But if I want a period, then I need to put this period somewhere. And then once my periodic structure like is there, yeah.
Sorry, but this line that you just showed, it would still be there in the absence of any explicit lattice.
In the absence of any explicit.
This would just be your purely spontaneous lattice. And this,
that's right.
This you can make.
Yeah. So one of the ideas.
It's the other line that would be absent.
So hopefully,
Hopefully
right now with some extra data collection, which is technical, I mean, it's relatively easy to do, we'll just see that this second line, depending on the amplitude of explicit breaking, will just go towards the origin or downwards. Because
it better go towards the origin.
Sorry?
I think it, okay.
Yeah.
I think it will go towards the origin.
It will go towards the origin when I reduce amplitude. It will go all the way to imaginary half plane if I increase amplitude. Like,
yeah.
The hypothesis is that this line would be controlled by explicit breaking, because if I want to interpret it as the friction of this periodic structure on top of my background, this would be the very natural explanation.
But I think both lines, I mean, even your other line, the Drude line, if you crank up your explicit breaking sufficiently high, then this blue line will also go down the imaginary axis.
Well, that's true, but it's
everything will go away.
That's not a problem. With these lines, they are trickier than you think. I mean, they can switch places easily.
Yeah, I know.
I mean,
we saw the same in these Q-lattice models.
Yeah, and for instance, in helices, which I couldn't show you now, the situation is exactly the opposite. So basically, this capital omega line is very close to the origin, but the gamma is deeper. Still, they do the same job. So the hierarchy of them can be switched.
Yeah, I think that depends on the details of your model.
Yeah, that depends.
The details of your ground state, more
indeed,
specifically.
I think that the point here, so my point here is that everything which you want to know about capital omega, you can learn from the normal state, like above the phase transition. And basically, depending on the features of your normal state, the second branch may either be here or may completely go away. And if it goes away, then basically that means that your system undergoes the phase transition precisely in the commensurate state. So without this incommensurate region. And that's basically the answer of how to interpret this plot and how to get rid of the extra coherent conductivity in this plot. But if it's true, then I would think that if it has something to do with commensurability, then it would be impossible to do that with homogeneous lattices.
Yeah.
So that's the statement. So the periodic model, it behaves in a way which is understandable from homogeneous lattice point of view when the amplitude is small. But once you go into commensurability regime, then it starts doing something extra, which we will see, because right now I haven't shown you anything. This is only my dreams that it will. But so far, it's quite surprising. It just follows this formula very, very closely.
Okay, maybe I'm letting the discuss. So, of course, we can discuss as long as, but if you want to show some conclusions or something.
I mean,
or
He
you're
doesn't
done.
have any. He doesn't have any.
don't
Stop
have any.
embarrassing him.
No, I was feeling bad. Okay, so
No more.
that's why I'm trying to stretch my time, no, because there's not.
No, the time is more than I was feeling bad because. No, okay, this is the good thing of the online seminar, so people can come and leave. Okay, so then sorry, keep going or not. I mean,
No, that was my conclusion. I mean, so this is a conclusion slide. This is a work for future, which I cannot discuss in much detail. But yeah, I mean,
very interesting.
this is the state of the art right now. So there were some discussions of whether periodic models will submit to this formula completely, and what is the meaning of capital omega there. So that's the answer. Yes, they do. So.
Very nice. Okay. So sorry for cutting you. So thanks a lot, and let's see if there is any question, of course, or comments. Nothing.
Oh.
Okay, one thing we will do from now on is I won't end the meeting. So if people want to keep discussing, some subset of people, I will stop recording. Actually, I stop now.